derivatives and integrals. We're going to start with derivatives first. Can anyone tell me what that is?
A derivative is a function that defines rate of change. It is the change of y over the change in x, so in mathematical terms, derivatives can determine slope. A derivative will most commonly be written in the form f'(x). According to online sources, derivatives can also measure the sensitivity to change of a function value, which is determined by the independent variable. Derivatives can be broken down into two components, geometric and physical. Geometric derivatives describe the slope of a line or curve, and physical derivatives describe the rate of change. The rate of change will be described as either increasing or decreasing. Derivatives will be very important when determining speed and velocity. Next is the tangent line. The tangent line is a component of derivatives. The tangent line also describes where the x value is close to 0. A tangent line to a curve is a line that touches a curve at only one single point. The tangent line is also a component of derivatives. The tangent line describes where the value x is close to 0. The Brown Math department offers great tips to find the tangent line. First, find the derivative. Next, plug in the x value, x of 0, into the derivative to obtain slope. Next, use x of 0 to find out the y-coordinate. Once the y-coordinate is found, use point-slope form to write the equation of the tangent line.
It's time to learn about integrals, which I know all about.
So you see, the velocity of the car was constantly changing. It increased when you first started and then decreased as you approached the stop sign.
Oh, so you mean the slope was never the same as I was going down the hill?
Exactly!
A long time ago, many scholars had a difficult time figuring out how to find the area of an object with a curved surface. One effort, made by the Greeks, was to keep filling up the area with bigger shapes and then eventually smaller shapes, like triangles. They would then calculate the area of the triangles to get a rough estimate of the area of the curved object. This is called the method of exhaustion. Then along came Newton and Leibniz. While Newton had good ideas on how to calculate the area, Leibniz's method was definitely more effective. This is where we get into integration. Integration is defined as the area of the graph underneath the curve. Leibniz found the area using a sort of picket fence method. Integral calculus combines instantaneous rate with the area under a curve. Integral calculus allows for the ability to find the area of larger shapes while plotting points on the graph. Integrals are found by adding the area of larger shapes together to get the bigger picture. To get a more accurate answer, more and more rectangles are added and shrink in size so that they will eventually fill up the space underneath more accurately. The smaller the width of each rectangle, the closer we get to the true answer. In a real-world setting, integrals can be used by architects to find the area of an arc by using multiple shapes to represent its area. Integrals can also be used to find the distance a car traveled over a particular amount of time. Integrals have many purposes, and this is just the start of our learning into the many functions that integrals can carry out.
Does that mean I can find the volume of this bottle?
You bet you can!
Math is fun! Yay!
So you see, the velocity of your car was constantly changing. It increased when you first started and then decreased as you approached the stop sign.
Oh, so you mean to tell me that the slope was the same the whole time I was driving?
It was never the same.
It was never the same. You're gonna be like